Hey everybody, welcome to part C of lecture 14. We're going to talk about correlation between variables as the first kind of inferential statistical analysis. But before I launch into the details of correlation analyses, I forgot to really tell you about these 4 items that we're going to cover. And I kind of lit out that at the end of the video a little bit too fast. So I wanted to give you the preview of what we're going to cover. So in correlation, which we're after right now, we're after doing an analysis which looks at, are variable 1 and variable 2 reasonably seen as having a relationship? Okay? And there are a whole bunch of different ways to do that. The second kind of inferential analysis is when we compare means of a group or maybe some other measure of a group between condition A and condition B, right? So we're like, what is the fasting blood glucose level for a diabetic who is in the control group or one which has been treated with this medicine? Is there a difference between the mean of control group diabetics and the treated diabetics? If so, then that would indicate that the medicine is the thing responsible for that, right? So that's a classical bit of inferential statistics. The next thing that we're going to cover is regression. Does change in one variable mean that there's going to be a change in the other? When X goes up, does Y go up too? And that is regression in exactly the kind of thing that you expect it to be, and most people have some experience with it, right? Okay, and the last thing is non-parametric tests. Now, many of the tools we will use for comparison of means or for making a regression assume something like the data come from a bell-shaped distribution. Or there are other techniques which are made for different shaped distributions where the data has say an exponential slope to it, okay, or something like that. But if we don't know which shape the data comes from, or if the data comes from a wacky shape that we know what it looks like, then we may go after these non-parametric tests. Non-parametric means we're not fitting it to the parameters of a normal distribution, okay? So non-parametric tests are made to handle wacky stuff, like counting numbers, okay? What if what we're working with is a variable which is about what place a racer was in a race, first, second, third, fourth, fifth? This is not normally distributed, okay? No numbers can be less than 0, right? And there's one person at every single point on this. So that kind of rank stuff is exactly how we generally handle non-parametrics, okay? But at any rate, as I mentioned, we're not really going to get into the non-parametric stuff during this lecture anyway. But I just want you to be aware of the fact that it exists. So let's get into correlation, right? What we're after is there an association, a relationship potentially between two variables? There are lots of different ways to do this kind of measure. The one that people generally think of when they say correlation is they generally mean Pearson correlation, also called Pearson's R, because we'll write it with an R as the representation of it, right? Spearman correlation and the chi-squared test are made for particular cases, right? And there's even other things like mutual information and things like that that are also measurements of association. So the unique thing about Pearson's R and why it's the standard is that it's highly related to drawing a line through the data, okay? If your data looks like you might be able to draw a line through it, and we have this independent variable x and some dependent variable y, and we want to ask ourselves, is there a relationship where y is dependent upon x, right? When x gets bigger here, then y gets bigger too. And if we think that relationship is fit by a line, that's where Pearson's R, or Pearson's correlation, is exactly the right measurement. Well, how so? So what correlation captures is there a strong relationship like this, where if we drew a line through there, that everything would be very tight on the line, right? So all the variance around that line is within relatively narrow band. Okay? Or is that line, which still exists, roughly the same line there, right? It just has much wider, much more variance around that line. Okay? So a stronger relationship yields a higher Pearson R value. Okay? So in this case, the R value might be something like 0.9, and in this case, it might be something like, say, 0.6. Right? So how does this work? Well, if as I mentioned there, the R value maybe on this is something like, say, 0.8, that's a positive 0.8. Okay? The larger the independent variable, the larger this x, then the larger the dependent variable, the one that depends on x, becomes. So anytime the slope of the line is like this, then it is a positive correlation. Okay, so a particular example is height of fathers and sons. The taller the father is, the taller the son is going to be, and the shorter the father is, the shorter the son is going to be. Right? This is still a positive correlation. Now, notice that the thing flipped over here, right? So now we have a negative correlation. In a negative correlation, as the independent variable becomes smaller, the dependent variable, y, gets bigger. So the slope is flip-flopped in these two cases, right? Now this is maybe still, what did I say it was back there? I've forgotten already. Okay, so we say that's 0.8, right? So then this is going to be a negative 0.8. Okay? So increasing x means decreasing y. So the more absences a student has, the lower the student scores. The lower the number of a student's absences, the higher their grades tend to be. Okay, this is a negative correlation example. So as I said, we're measuring using Pearson's R. And Pearson's R is unique in that it's about addressing a linear relationship. If you can draw that line through it, Pearson's R is the right way to measure the correlation. R value takes between -1 and 1. Okay? When something is, actually there's another formulation of Pearson's R, to be fair, which goes to -infinity. But 1 is always the highest value that Pearson's R can take. A 1 means that two things are perfectly correlated. That is, that they fall straight under a line. Okay? And drawing a line over the data completely hides the data points. That is a perfect correlation of 1. Okay? A correlation of 0 has no line at all. It's just a blob. Okay? So that is not correlated. Right? And so this correlation, -1 to, this version of Pearson's R, -1 to +1, what we have is a -1 is a negative line here, a negative slope. That's exactly a perfect line. And then as these dots get wider and wider around that line, and it gets towards a blob, we get to 0. And then as the dots coalesce again around a positive slope, then we get to 1. Okay? Again, correlation is how close the data is to being in a line. It's not what the slope is. The slope could be, like this, or like this, or like this. As long as the data lies close to the line, the value of correlation is close to 1. If the data is spread out around the line in a great huge channel, then the correlation is closer to 0. Right? So this illustrates exactly what I was saying, right? See, these data here are all relatively close in around the line. These data here are pretty far away from the line in comparison. So the top row is 0.7, 0.3, and 0, which is just, again, a blob, right? 0 is just a blob. It doesn't have a line, really. Okay? And these are the negative correlations. The same deal, right? The same level, the number, the numeric value indicates the spread. Negative 0.7 and 0.7, they really have the same narrow band. It's just whether it's a positive slope or a negative slope. Okay? And 0.3 and minus 0.3, they're both pretty spread out around that line. It's just positive slope, negative slope. All right, so that is correlation. Correlation is a measurement of how tight the data fits a line. Now, the thing about all metrics is that they can be fooled. If I remember correctly, we've already brought up Anscombe's quartet in this class. But if I haven't, my apologies. It is a very fascinating set of counterexamples. Right? So it's great to measure the mean of a data set. It's great to measure the variance, right? The central tendency of the data is the mean. The variance is the spread around that mean. It's great to measure the correlation between two variables, right? That x and y are highly related. But if your data doesn't meet certain kinds of standards, then it's possible to have 4 or more different data sets that all have the same measurements, right? They all have the same mean. They all have the same variance of x and variance of y. They all have the same correlation between x and y, which is a relatively high correlation value of 0.8. They all get a linear regression that has the same slope. Okay? But as you can see, they're very different data sets. Now, why is it that we can do this, right? Only the first data set is what we would call a proper data set for doing linear regression on. Okay? It meets the right kinds of criteria for a linear regression. This is not a line, that's a curve, right? So linear regression and linear techniques like Pearson's correlation, which is about stuff being close to a line, right? They don't work for this. And that's why we can get a measurement here for variance and for a correlation coefficient, which are identical to the number 1 data set, right? Because this violates the rules. Okay? So does this other, this is 2, 3, and 4. All 4 of these, all 3 of the others, 2, 3, and 4, they all violate some aspect of what we expect out of the data in terms of its linearity or its normal distribution of residuals or stuff like that. Okay? And because of that, we have 4 data sets that all have the same measurements. So this is a cautionary tale. The reason we talk to you about Anscombe's quartet is, first off, always do your descriptive data exploration, right? If you don't make the histograms, you can't know that data is wacky like this, all right? So you need to do that to find out if your data is wacky. Secondly, we tell it to you because you need to know the wackiness. You need to not just see it, but know that because of that wackiness, certain kinds of inferential statistics are not appropriate, right? If things don't look like number 1, if they look like 2, 3, or 4, then you can't really apply linear regression or any techniques that come from that same world, like Pearson's correlation. All right. So this is the part where you get to participate. Tonight I am not going to put up the quiz. I'm sorry. I'm going to make you do the thinking in your own mind. Okay? So take a moment. Ask yourself, maybe write down on a piece of paper, right? Which of the following measurements of Pearson's R is the right one to describe this data set? So note that you have negative and positive values. So maybe that tells you, maybe the line tells you something about which ones of those it is. But you also have to guess whether the tightness of the data indicates a little bit of a narrow thing around the line or a little bit wider, right? Which way around is it? Well, it's a 1 means it's tight, tight, tight on the line. And a 0 means it's a blob. We don't have either of those. So the answer is that we are going to be on one of the 0.64s. Now, is it a positive slope or a negative slope? Bueller? Anyone? Yes, it's a positive slope. Okay, that's correct. So it's the correct answer is D. Okay. So here is another example. What about this one? Oh, look, my camera decided to stop working. Lovely. All right, you can't see my face the rest of this time. So what's the Pearson correlation coefficient for this relationship? Well, it's still a positive slope. This one's a little bit tighter. So this is E. All right, what about this one? Positive or negative slope? Yes, you in the big hat. Yeah, it's a negative slope. Okay. So what about the spread? Is it a number close to 1 or a number not quite up that high? Let's find out. Yep, not quite up that high. All right. So we all know this, right? I mean, it's like such a trope. Everybody knows that correlation is not causation, right? But yet people often make this mistake, not because they don't know this, but because if they're not cued to think about the problem, it's easy to just kind of let something slide. Somebody shows you a pretty graph, and this graph, the bumps on it, seem to line up between the red line and the black line, right? So the bumps seem to line up, that we have the number of drownings in pools is really closely aligned with the number of films that Nicolas Cage appeared in. My real question is the number of films Nick Cage appears in driving drownings, or is it the other way around? All right, so clearly this is something called a spurious correlation. there can be no relationship between Nick Cage's performances, as psychotic as they may be, and how many kids get scared and fall into swimming pools and drown. No, that doesn't happen, right? And you can go to this website that you can see on the lower left. I highly recommend it, and you can find all kinds of spurious correlations of your own from the data that is presented there. All right. So, divorce rate in Maine has absolutely nothing to do with consumption of margarine, is another example. And yet, this correlation is nearly perfect. Okay? I will also mention, sorry, I should go back to that. So, this seems silly. And you laugh a little bit because, again, we all know that correlation is not causation. But let me tell you, I cannot say how many people I see publishing things about COVID-19 where what they show is they show an increase or a decrease in levels of COVID prevalence in an area, and some other line that moves up and down together with it. And that some other line, they say, like, here's clear proof, right? That this other thing is what drives the increase or decrease of COVID incidence. See, that's exactly what I mean, is that if I asked you if correlation was causation, you would be able to tell me, no, duh, it's not. But yet presented with evidence like this, about something that people really care about, that is important to them, right? They have some sort of reason to be looking for an answer and really motivated to find one, right? It's easy for people to just kind of let that fly out of their minds and not look at the claims of a given journal article on this stuff seriously and completely. All right? So just FYI, I'm not saying that all the research on COVID is BS. I am not saying that, okay? What I'm saying is that oftentimes somebody who thinks about statistics and analysis in a sophisticated way is understanding these papers very differently than somebody who just comes in and posts them all over their Facebook. All right. So that is all I had for you on section 1 on correlation. Next, we're going to look at how we compare means of two different groups, right? And maybe in the middle of all this, I'll fix my camera and you'll have a view of my pretty face again. But if not, I will see you some other point. Bye for now.